Welcome back. This video is going to cover the topic of lags, especially lagged predictor variables. We will use lagged predictor variables whenever the predictor variable could have a delayed effect. So this is very common in marketing and IMC with, for example, advertising. Perhaps the advertising I do today changes your attitude, and that attitude change persists long into the future. There are some extremely powerful brands like Coca-Cola and McDonald's, and part of the reason they're so powerful is because of the advertising they've done over the years. So the advertising I do today could have an immediate effect on you, but then it could also affect you next month and the month after and the month after that. There are many examples of where there could be delayed effects. So one of the kind of classic textbook examples is rainfall on streamflow. So if you have rain falling today, it enters the groundwater somewhat slowly, and some rain that happens today may take days to show up in a stream, or downstream in a river could take even longer. Another example that's very much top of mind is COVID cases on the death counts. So a couple months ago, there was a fairly strong relationship. The more cases you had this week meant a higher death rate, say 2 or 3 weeks down the line. That's gotten a little bit more complicated. So now we have other issues around the ages of people contacting the disease, as well as different issues around how much testing gets done. So it's not quite as clear as it was earlier this summer. That would be another example where the more cases that are detected is a leading indicator that there will be higher death rates in the future. The way we will do this is to include a lagged version of the predictor variable in the model. So we could have, for example, the level in the river is a function of how much rain we got last week. We could also have this week, we could have the week before, and so forth. Now we can write this in backshift notation as follows. So this would be gamma naught times xt, gamma 1 times xt minus 1, and then gamma 2 times xt minus 2 when you apply the backshift operator twice. We can think of this whole thing as being a single function. So we could call this a function of gamma. And this is going to be called a transfer function since it describes how the x's get transferred into the y's. When we fit these models, there's a very important assumption, and that assumption is that only x can influence y, but y cannot influence x. If we're worried about those sorts of issues, we're going to need to have other models. A fair question is whether this is true about advertising. The reason I question this is often the advertising level that you have next month is in part determined by your sales this month. So if advertising is just a percentage of sales, the more sales I have this month, the more advertising I do in subsequent months. But let's not think about that for right now. Well, how do we pick the number of lags? There's a number of issues around this. So one approach is that we just start adding lags until by adding an additional lag, the next one is insignificant or it causes our corrected AIC to increase. So that's called the bottom-up approach. There are some practical issues, though. The first one is typically you're going to have horrible multicollinearity problems. The reason for this is your advertising is just a percentage of sales, and your sales are fairly constant over time. Then your advertising is fairly constant over time. Advertising this month will be highly correlated with advertising last month and the month before. And what you'll see is that the regression's just going to melt down. You're going to get all sorts of crazy sign flips. It's not going to be good. So you want to look at your VIFs. You want to do robustness checks where you see if I didn't have, for example, advertising this month, what happens to advertising last month? If you have them both in there, what happens? So you want to be doing a lot of those robustness checks. There are also issues with multiple comparisons. So if we end up doing a lot of significance tests at, say, the 5% level, just by chance, some of those tests could be significant when, in fact, the null hypothesis is true. So that's the multiple comparison problem. So for example, if we did 20 tests where the null hypothesis was exactly true, so maybe 20 tests on predictors and all of the predictors have a zero effect. Well, just by chance, we would expect one of those to become significant if we do our tests at the 5% level. So 1 in 20 we would expect to come up significant. So that's another issue. I think a bigger one is the multiclinearity issue. We're also burning up a lot of degrees of freedom if we include many distributed lags. So I'd now like to take us through an example. This example is called the North Carolina sales example. I've taken it from a book on SAS's time series modules. The book has a lot of very interesting case studies in it. I don't like the SAS time series software as much as I like ours, but there are a lot of good case studies in this book. What we want to do is model how the sales of some focal firm depends on its advertising this period as well as last period. And we're also going to worry about competitor sales as well. So I'm going to read in the data, and what we have are a handful of variables. We're not going to be using all of these. If we look at a correlation matrix, what we see is that advertising this period has a substantial correlation with advertising last period. I would almost say this correlation of 0.59 is a bit on the low side. In my experience, those correlations tend to be even larger than that. But I've used this example specifically because this correlation is not so overwhelming. Let's go take a look at how advertising is related to sales. And so we see the more we advertise this period, the more we sell this period. But there's a negative correlation, a small negative correlation between what we did last period and our sales this period. We also see a very large correlation between competitor sales and our sales. So the more the competitor sells, the less we sell. So it looks like these are very much substitutes. Let's now take a look at the time plot. And what we see is something that may have a slight positive trend. It looks a little bit cyclical. It's entirely plausible that this is stationary. So let's go test for stationarity. And what we see is that we have a p-value that's somewhat borderline. It's somewhere between 5 and 10% significance level. Let's treat it as stationary for right now. Remember, the remedy for this would be to take some differences, but let's not do that now. So I'm going to start with a linear regression model, but I'm going to not have the competitor sales in the model. We really shouldn't be interpreting this until we've looked at our residuals, though. So let's go first check those out. And so what I see with the residuals is a lot of problems. So with this time plot, we see that the residuals are mostly negative, then they become mostly positive, then they're entirely negative for a period, then they're almost entirely positive for a period. This is not the proverbial snowstorm that we want to see with our residuals. When we look at our ACF, we have a lot of very large correlations, autocorrelations between our observations. The assumptions of this model are violated. When we go look at our test for serial correlations, the p-value is tiny, so we're going to reject the null hypothesis that we have no serial correlations up to order 10. So this model is not adequate. One cause of this could be an omitted variable. The omitted variable is competitor sales. So let's go bring that in. Now, again, we ought to go look at our residuals first. And what we see with the residuals is they're looking a lot better. So I don't see any systematic patterns. That's pretty much a snowstorm. None of my autocorrelations are significant. Residuals are normal. And the Broish-Godfrey test has a p-value that's massive, so I cannot reject the null hypothesis that my first 10 autocorrelations are all 0. So I think we've got a reasonable model here and one that's worth interpreting. So let's go look at the summary. Now, what we see with this summary is something very interesting. Let's start with the obvious one. The competitor sales has a very strong negative effect on our sales. So the more the competitor sells this month, the less we sell this month. So again, there's direct competition. We also see that advertising helps us a lot. So the more advertising we do this period, the more we sell this period. However, the more advertising I did last month, the less I sell this month. This is almost as if what's happening is I advertise and consumers do forward buying and they stock up. And so if I do a lot of advertising last period, that means I'm not going to sell much next month. Now, I'd like to do one more thing with us, which would be the following test. So let's go over to my document camera, and I'm going to write this out. So this is really my model. Sales is equal to, let's just say beta naught plus beta 1 times ads. We should probably stick a subscript t in here. Then plus beta 2 times add t minus 1, or you could call that lag t if you like. And then we've got beta 3 times the competitor sales at time t. And then there's really some errors in here as well. So the hypothesis that I'd like to test is whether it's plausible that this beta is just the opposite of this beta. So I'd like to test H naught beta 1 is equal to negative beta 2. So is it possible that whatever the effect of advertising is this month cancels out with the advertising I did in the previous month? What I'd like for you to notice is that this would imply beta 1 minus beta 2 has to equal 0. The way we can test this in R is with the general linear hypothesis test that we covered back in my machine learning class. So I'm going to fit another model where I include a term that constrains these coefficients to be 0. So this model would look something like this. Sales t is equal to beta naught plus beta 1 times add at time t minus beta 1, so that has to be exactly the same coefficient, times add at time t minus 1. And then let's keep calling this beta 3 times the competitors at time t. So notice this whole thing is just beta 1 times add at time t minus add at time t minus 1. So this is a reduced model that puts on this constraint that the effect this period, beta 1, is just negative the effect for the lagged version. Let's go fit this, and you can go see what you end up with. You have now a combined beta, and the competitor effect is roughly the same. What I really want to do, though, is an Anova test. And so when I run the Anova test, there is 1 degree of freedom difference. So the degree of freedom difference is beta 2. So beta 2 is no longer in the model. Beta 2 has been replaced with negative beta 1 here. So this is what we had as beta 2 before. So that's the one degree of freedom difference. What we see is that our sums of squares increase by this amount when we add that constraint. So when we reduce the number of degrees of freedom by 1 from going from model 1 to model 2, this is how much my sums of squares go up. So if you don't believe me, let's go try this. If I take the deviance of fit 2, that should be higher than the deviance of fit. And so you will see it increases by exactly the amount that I claimed. Now the units are very big here, so even though that looks like a big number, when you divide by the mean squared error of the full model, so that would be model 2, you get an F that's actually pretty tiny. And the p-value is not significant. Let's just go write this up. The p-value is 0.076. That's greater than 5%. So we cannot reject H naught beta 1 equal to negative beta 2. So in other words, it kind of looks like whatever advertising we do this period offsets what we did in the previous period. I'd now like to go over a model that's very important in marketing science and IMC called the Koyck model. The Quake Model is used to understand how advertising over time affects some outcome that we care about, like sales. Let me begin with an important assumption that the Quake model is going to make. So the Quake model is going to assume that the effects of advertising in previous periods all have the same sign. And so we'd like for that sign to be positive, where more advertising means more sales. That's one assumption. The other assumption that we're going to make is that the effect of advertising is going to decay geometrically. So it's kind of like the damped trends that we studied with the Holt method, where the effect decays geometrically over time. So this is going to be the model that we assume. Our sales in time period t is some constant, so think of this as an intercept, plus a beta. So beta is going to be a slope, so it's the effect of advertising, if you will, times this is what advertising is. So we're going to give the current amount of advertising full strength. Then the amount of advertising that we did one period ago gets multiplied by some coefficient that's usually less than 1 phi. What we did 2 periods ago gets discounted by phi squared. So let's just say, for an example, that phi were a half. Then this period's advertising counts full strength. Last period will only count a half. What we did 2 months ago would count 1/4. What we did 3 periods ago would be 1/8, and so forth. So what we did many periods ago might have a tiny effect on our sales this period, but because it gets multiplied by a phi to a big number, it's almost negligible. And then there's some errors. These phis are called the retention rate or the rate of decay. So how does advertising decay over time? And we can call beta the short-term effect of advertising on sales, although we're usually more interested in a different effect, namely what we call a carryover effect. So this has to be interpreted relative to all these previous advertising effects, and we're going to try to bake that into this carryover effect. So let me go over that now. Let's think about my advertising this period. Well, my advertising this period will get full strength, but then what I did this period will actually have an effect next period, except it would get multiplied by phi. Okay, so if you were, say, a half, then it would come in at half strength next period. Then 2 periods from now, it would go down to phi squared or a quarter if phi were a half. The effect of advertising this period is going to have this geometric series over time. So this will be, think of this as the total effect of advertising into the future, and then we're going to multiply that by this beta. So beta is whatever my advertising effect has into the future. Now we recognize what I've highlighted as a geometric series. So this is going to sum to 1 over 1 minus phi. So take 1 over 1 minus phi times beta, you get beta over 1 minus phi. So we can think of this as the total long-term effect that $1 I spend on advertising this period will have on sales into the future off, an infinite number of periods. So this is usually the quantity that we're much more interested in. Well, I'd now like to do some algebra on this. So my algebra is going to be as follows. Let's subtract the quantity phi times y sub t minus 1. So this is, you can think about almost like an autoregressive process. I'm going to take phi times what my y was last period. So let's go do that to the left-hand side. And then what I do to the left-hand side, I have to do to the right-hand side. So I copied exactly what I had up here. Now let's go right in this second term. So phi times whatever this is for 1 period ago. Well, that's going to be minus phi times c. Then I'm going to have minus, we're going to have a phi and distribute it across everything in there. So this would be, instead of xt, it's going to be xt minus 1, but I have to multiply it by t. And then instead of xt minus 1 will be xt minus 2 times phi squared and so forth. And then I have to take phi times the error from this equation evaluated at time period t minus 1. Well, the beauty of this is a lot of stuff cancels out. So what I see right here is I have beta times phi times xt minus 1. Well, what do I have here? I have beta times phi times x minus 1, so those two go away. What's the next term? Well, I have beta times phi squared times x t minus 2. What do I have here? Well, beta times phi squared x t minus 2. So these two terms also cross out. So basically everything in this parentheses cancels out with what I have up here, with one exception. And that one exception is the first term. So there is no xt in my equation for yt minus 1. So let's go collect some terms. I end up with c times 1 minus phi times c. So we can pull the c out. This is just c times 1 minus phi. Then, okay, we've got to keep this term. And so we've got a beta times xt. Then I've got my error term, epsilon t, and then I have minus phi times epsilon t minus 1. So what I'd like to point out is this kind of resembles an Arima model. So we have one autoregressive term, and I have one moving average term, but it's not quite the Arima model that we've been studying. So what we've been studying is regression models, so yt is some function of xt, with Arima errors. So remember, I was calling those etas before. I don't have that here. And the etas are what receive the autoregressive treatment, not the y's. So this has another name, sometimes called an Arima X equation, that is not estimated with the Arima package that is in the forecasting library. There's some additional libraries that have been added since forecasting that will do it, but we're not going to get into that. So just be really careful. This is not a regression with Arima errors that we know and love from Chapter 9. This is something else. And I'd suggest reading there's a blog post from Heinemann that kind of points out the difference between these. These Arima X models are substantially more complicated, and so we're going to kind of avoid it. All right, well, how are we going to estimate this? The answer to that is somewhat complicated. So there's an article by Francis and Ust that you can go read that's specifically written about how to estimate this. So this article points out these issues, that it's kind of like an Arima 1.1 model, but you have a very strange constraint, is that the moving average term has to be the opposite of the autoregressive term. So that's very weird. So what a lot of marketing science textbooks will tell you to do is just use OLS. So ignore the moving average part, regress yt on yt minus 1 as well as x, and don't worry about the moving average. Well, this Francis and Ust article find a downward bias when you do that, and they call it not a sound approach, even though you'll see it in many marketing science books. The second approach that Francis and Ust will consider is what they call the unrestricted Armax model. And so the idea here is we're going to fit an autoregressive model in terms of y, not in terms of etas, but in terms of y. And we're also going to fit a moving average term for my errors. And we're not going to introduce the constraint that theta is the opposite of phi. So remember back here when we did the algebra, the autoregressive coefficient phi equaled negative the moving average term. So we're just going to kind of gloss over that and let the model estimate whatever it wants. Now, Francis and Ust do some simulations and find this to be a pretty promising method, that it leads to almost no biases. So let me re-emphasize what I said before. So what I was saying up here, that this is not a regression with Arima errors, you can't just, it'd be really tempting to estimate an Arima 1.0Q model in ARM, but that's not true, because this would be autoregressive in terms of eta rather than y. Instead of downloading yet another package, we're going to do it kind of a kludgy way by including the lag of y as a predictor. So that's how I'm going to recommend doing it. Francis and Ust also talk about another approach. They call it the restricted Armax approach, where you explicitly add this constraint to your model, find the maximum likelihood estimator, and they prefer this, although they don't get into the details of how exactly they make this work. So I've had some difficulty in duplicating it. We shouldn't worry about that here. What you should take away from this is kind of complicated, but despite all of these problems, this is a very important approach in marketing that you need to know about and you'll encounter when you fit sales response models with marketing mixed variables. I'd now like to take us through a case. So this case is going to address what I think is one of the holy grails of advertising and marketing, which is brand equity. So brand equity is something that builds up in the consumer's mind with the associations they have towards a brand. And these associations are often formed through the advertising the brand has done over the years. So there are many very famous examples of this. For example, why does Coca-Cola have such a high stock price? Part of that reason is because of the brand equity that they've built up over the past over 100 years in the advertising they do. Of course, what happened 100 years ago probably doesn't matter so much today because no one is alive. We don't need to get into this. So does advertising today increase sales in the future years? Before we get into this, let me issue a word of caution. So this is a word of caution that I made before in machine learning about models that are interpretive. You should start with a conceptual framework. So what are the factors that would affect, in our case, sales? And make sure you have those in the model. So, for example, there may be other things affecting your sales, such as price, and what you want to avoid is the situation where maybe price and advertising are confounded. Whenever you advertise, you lower your price. Whenever you reduce advertising, the price goes up. In that case, the effects of advertising might be confounded with the effects of price, and you would come to the wrong conclusions about your advertising. So start out with a conceptual framework, get measures of the relevant variables in the model, and fit that model with an appropriate estimation routine. I'm going to take us through a very famous case, which is the case of the Lydia Pinkham company. So this data set has been analyzed in a lot of different papers. So it's analyzed in the Francis and Rist article. I've given you a couple other links to some articles that have analyzed this over the years. So it's very much worth checking out some of those other analyses of this data. So what's Lydia Pinkham? If you click on this link, you will get the Wikipedia page. And Lydia Pinkham made an elixir that had herbs and alcohol in it. And it was targeted at women. So you can read all about this on the Wikipedia page. Now, one of the real interesting things about this data set is that Lydia Pinkham sold one product, so the sales of the company would not be affected by other things they sell because they don't sell anything else. And their marketing mix was fairly consistent over this very long 50-some year period of time. So that's probably one of the reasons why this data set gets analyzed so much, is because you don't have a lot of confounds and there were no real direct competitors to this elixir. Another thing that's going to be very interesting about this data set is that part of the time span covers a period in U.S. history called Prohibition. So Prohibition was a period where alcohol sales were forbidden, and Lydia Pinkham, not being like vodka or whiskey, could still be sold. So what's very interesting when we look at a time plot, here's their sales and their advertising. You're going to see their sales go way up during this Prohibition period, probably because a lot of people who wanted to drink alcohol but couldn't buy it turned to Lydia Pinkham and they started drinking this herbal elixir in order to get their alcohol. All right, so we're going to be looking at the effects of Prohibition in a later video when we talk about VAR models. So you'll just have to wait for the next video for that. Well, let's go over to R and run this one live. This data set is available in a library called m, A, r. Let's go make our autoplot. And so this is the autoplot that we just saw. What we see is that advertising and sales resemble each other. They kind of follow each other. When advertising goes up, sales go up. When my advertising goes down, sales go down. And so they very much track one another. One policy that companies often follow, and I really don't know what policies Lydia Pinkham followed, but say advertising is often set to be the percentage of sales. So take a couple percent of whatever your sales are, and that becomes your advertising budget for the next year. So that could be in part what's happening here, but it could also be that advertising, we spend more on advertising and our sales go up. The first thing that we should worry about is the stationarity of these data sets. If I go run the KPSS test, what we're going to see is the test statistic for sales is pretty small, so we're not going to worry about the stationarity of sales. If I look at the one for advertising, I come to similar conclusions. So no serious problems with non-stationarity. The next thing I want to do is I'm going to create a new version of this data set with various lags. And so what you'll see here is I'm going to create a couple lags for advertising, and I'm going to create a couple lags for sales as well. So let's go let that run. And let's go take a look at our correlation matrix now. What you will see in this, I think, is very typical of data sets I've looked at where the correlations between the ad variables are pretty substantial. So the correlation between my advertising this period and last period is about 0.82. It's like think of it like an autocorrelation for your x variables. What I do this period with what I did 2 periods ago is pretty highly correlated as well. You see a similar 0.82 between last period and the period before. And so this is telling me we're going to have a multicollinear mess on our hands. Now, another thing that I think we should note is advertising has a positive correlation with sales. However, that effect diminishes over time. So my advertising this period correlates with sales this period with the value of 0.84. What I did last month has a positive correlation, but it's only 0.71. What I did 2 months ago only has a correlation of about 0.5 with my sales this period. So this is entirely consistent with the assumptions of the Quake model. So remember, the Quake model assumes that these coefficients will all have the same sign, which they do, and that they're going to decay roughly geometrically, and I kind of hope that's what's happening here. So it kind of looks like that's a reasonable thing. I'm going to add prohibition as a variable. We're not going to do anything with this video. Likewise, we'll add some years. We'll take care of that later. Another thing that you usually want to do is take a quick look at your data set and make sure you did it right. So I find the lag somewhat confusing in R. So I like the lag function in dplyr for that reason, and so I did my lags correct. That makes me really happy. And you can see prohibition is now a 0,1 variable that takes the value 1 if it's that period where alcohol was illegal. Well, let's start out with just fitting a distributed lag model with OLS. So I'm going to regress my sales on advertising this month, last month, and the month before. Let's first start with our residuals. And so I'm not happy. The reason I'm not happy is the time plot is showing some definite patterns. So they're systematically positive, systematically negative, systematically positive again. My ACF is a mess, so that's not good. The Broish-Godfrey test is also very highly significant, so I can reject the null hypothesis that all of my autocorrelations are 0. So I've got some problems. With that said, let's just go take a quick look at my regression coefficients. So remember, these regression coefficients are going to be unbiased, but I'm not going to trust the standard errors. I'm not going to trust the t-statistics or the p-values a lot. So what I see here is fairly large positive effect for current sales, not much in terms of lagged effects. They're not significant, but I don't trust them. Usually, when you have a correct model, the p-values get larger And so what I'm seeing here are giant p-values that are only going to get larger once I use the correct model. So I don't have a lot of evidence for saying that advertising has a lagged effect. So this is kind of bad news for the brand equity group, that maybe there is no long-term effect with Lydia Pinkham, but we're going to need to do some additional analyses on this. If I go look at my VIFs are horrible. Remember, values above 5 are considered large. Well, we got a value above 5. We got a bunch of values in the 3s, which makes me nervous too. So this is a not a good model. What we could do is try to at least fix the errors. That's not going to do anything about the multiclinearity, but one way we could do this is use my auto Arima function to fit a regression model with Arima errors. So let's go look at our residuals. I see a lot of improvement. This is, my ACF is looking pretty good. I've got one significant autocorrelation, but that could just be spurious. It's very borderline. Maybe I've got a little bit of a pattern up here where all the residuals are positive, but this is looking a whole lot better. So including 2 AR terms for my errors helps me a lot. My p-value is borderline significant, not quite significant. So this one's substantially better. We could, just eyeballing this, I see this last lag is nowhere near significant. So I might try dropping that. So notice I've gone from columns 4 through 6 as predictors to just columns 4 and 5. And so let's go look at our residuals. And what I see here still keeps the two AR terms. My p-value for the Young box test is nowhere near significant. None of my ACF values are significant. So I think this one's actually a pretty decent model, just with these 2 add terms. What I see is dividing 0.53 by 0.13 is, what is that, about a t-statistic of 4-ish. So that's going to be very highly significant. If you take 0.2 divided by 0.1, you get is about 1.69, and so that's going to be almost borderline significant. So we've got a little bit of evidence that there's a lag effect of advertising, but it's not very convincing. Let's go now fit a Quake model. I'm going to start with an OLS model. Remember the way we fit our Quake model. Let me just take us back here to this. The approach is to regress yt on lag y and your current x. And we're going to ignore the moving average part. Here's how I fit that Quake model. So sales is a function of lag sales, and then my advertising variable. And let's go see what we have. We see a very strong effect for lag sales that usually soaks up a lot of variance. T-statistic is about 8.3. And we see kind of a borderline significant add effect, but I probably shouldn't be interpreting these p-values until I check my residuals. So my residuals are not looking good. We have quite a few significant autocorrelations. I'm seeing quite a few patterns in the residuals, and this p-value for Boyce-Godfrey is significant. It's almost highly significant. If we check for multiclinearity, we've still got a moderate amount. We have some values in the 3s. At least we don't have that value in the 5 anymore, which was, I would say, pretty problematic. Well, let's go estimate the carryover effect. So the carryover effect is going to be the advertising effect divided by 1 minus the lag sales effect. So if we go look at this, the advertising effect is 0.32 something or other. The sales effect is 0.75. So let's just go see what we have. The carryover effect is about 1.37. So let's just remember that. In fact, I think I might just go leave a note for myself here, 1.37. So if we go back to the course packet, that's just going to be the, if I put $1 into advertising, I get $1.37 back in sales. So that's a pretty good effect. Now, I don't get all of that today. Some of that is going to come in a month, 2 months from now, and so forth. But that's the carryover effect in the equation. Well, what I'd now like to do is try estimating this a different way, which is this unrestricted Armax model. So the way I'm going to do this is to include columns 2 and 4 from my data set. So let's just go look what's in pink 2. You're going to see column 2 is lag sales, and then column 4 is my advertising this period. So this is exactly like the model that I had before, except that I've got an autoregressive effect for y, not for eta, but for y. And I'm going to use order 1. So I'm just going to set this to be 1 because that's what our theory has really told us. We are supposed to have one moving average term in there. So let's go try this. If I look at my residuals, they're not great. I'll be honest with you, they're not great. So there's systematically positive residuals. I've got a couple significant ACF values, more than I can just write off as by chance. And then my Box-Young test is very highly significant. So I'm not completely happy with this, but let's go look at the coefficients. And so what we'll see is that here's my advertising effect. This is the sales effect. And so if I take advertising divided by 1 minus sales, so that's what I've done up here. Advertising divided by 1 minus sales. We end up with a carryover effect. Let's call this 1.30. So if I round to 2 decimal places, that would be 1.30. Let's just say carryover, because that's one word. And so that's roughly the same as the OLS estimate, not wildly different, and I guess that's believable. So I suspect the real effect of advertising is somewhere in this neighborhood of around 1.3 something or other. I don't quite know which one is right. I probably trust the Arima model more that I just fitted over the OLS model, because at least we're theoretically justified here and making some effort to account for the moving average part in our errors, even though the model doesn't fit that well. I thought I would mention one project that I got involved with that applied this Quake model to a different situation in marketing. The situation is with customer satisfaction. Very often we have multiple interactions with the firm. So for example, maybe I go to a coffee shop a couple times a week. So every time I go to that coffee shop, I have a service experience. Some days, though, the service experience is really good. Other days, it may not be quite as good. And what happens in my mind is that all of these different service episodes will kind of average together and form my current level of satisfaction with this coffee shop. So the way we thought about this was as a Koyck model. Every time I have a service encounter, I have a certain level of satisfaction, and this satisfaction will affect my future transactions with the firm. So whether I come back to that coffee shop or not. What we assume is that more recent service episodes will have more effect on my future behavior than episodes that happened long ago in the past, and that the decay follows a geometric pattern as with the Quake model. So if you're interested in reading this, you can see where my share of wallet, so how much I purchase at the focal firm, is a function of what my current satisfaction is, as well as a lagged version of my share of wallet. And so this is exactly the Koyck model, except that we also include some random effects. We ended up estimating this, and what you end up with is exactly that long-term carryover effect, which is the carryover effect of my long-term satisfaction on future purchases. If you're interested in this, it's, I think, a very well-written article that shows a different use of these Quake models.